So thank you very much for inviting me, Bruce. It's a pleasure to come and talk here. Bruce was very open about what I could talk about, so I cast around and looked for a topic that I hope would be interesting. As a scientist, mathematician, physicist, whatever label I'm choosing for the day, whenever something, I get really excited about it, and whenever I talk about it, someone goes, "But what's it useful for?" And I'm like, don't even think like that. What's the Mona Lisa useful for? You know, let's think about how amazing this is, how beautiful the achievements are, and that's what I want to try and share with you a little bit today. So, a bit about me. I'm a former Christian. I'm continuing to seek the truth. Some of you are probably unfortunate enough to know authors. Some of you may be even more unfortunate to be an author. If that's your case, you'll know that authors like to talk about their books. So this may come up once or twice more, but I'm the author of Evidence Considered. I have a PhD in physics. My physics is low temperature condensed matter physics. So not exactly related to evolution, but I'm sort of giving the physicist take on it. So the reasons that excite me, the reasons that evolution excites me are not maybe the same as a proper biologist or something, but it'll be fun. So the idea of beautiful evolution, I think, as part of the triumph of humanity, is that we have things like Shakespeare's plays and the music of Bach and the Da Vinci's art and Van Gogh's art, and I think it's just we should celebrate them just because of how amazing the humans are who created these things. Figure these things out. So I've got three things I want to talk about. The first two are sort of relatively specific experimental results that I think are kind of remarkable. So one is common descent in our DNA, the other one is apes in our chromosomes, and then the third one will be substrate independence, which will be a little bit more philosophical, I think. And we'll hopefully, I'm not going to try and defend that one as much, but hopefully we'll get some conversation going. So, common descent. Richard Dawkins wrote a beautiful book called The Greatest Show on Earth, and one of the chapters discusses this idea. I've got my own take on it to try and hopefully explain it. So many of you may know the idea, but I think it's always worth revisiting. So, I'm going to begin with an analogy, and we're going to take 10 cars. Here they are. Okay, we're going to assume that these are sort of modern cars, all a little bit different. All have internal combustion engines, and we're going to look at a single component of this car. So let's say a fuel injector. Each of these cars has a fuel injector, but of course they're recognizably the same. Each one has a function that's recognizably a fuel injector function. People who are expert in this would know, but they're also different. And with these differences, we're able to infer a tree. Okay, so the tree is really just a way to explain the similarities and differences between the components of these cars. I'm not necessarily inferring any meaning, but this is what I mean. So suppose we have some feature that exists on the right three components, and it's different on the left 7. Right? Then we would make our first divide there. So that's the top of the tree. Then we say, okay, well, the one on the far left is different, the other 6 can all be categorized, and so we divide it again like that. And then we do the game 3, 3, and then 1, 2, and we just keep going through until we've inferred a tree. Okay? So that's everyone must be so far. We've just inferred a tree based on similarities and differences. Now, with a different component, fuel pump, you might expect to get a different tree. Okay. So I'm going to make a mistake that I was once in a talk listening to, and the person here's what I'm about to do, and it was a great error because I switched off for the next 20 minutes. He asked a question about combinatorics. So, how are they? So if you are one of these people who's tempted to work on it, just pause. I'll remind you after the talk that you can come back and work out how many possible binary trees there are with 10 different elements. We think there's around 1,000. 10,000. 100,000. Million. 10 million. Any guesses?
I'm going toward the larger numbers, but I'm not exactly sure where to put it.
2 to 10-ish? 2 to the 10-ish. That's a pretty reasonable tape.
I'm thinking it's bigger than that.
Yeah, it's a bit smaller actually. So it's about 34 million. 34 million.
Oh,
There's about 34 million different possible binary trees. When you, and as I say, don't think about it now. I'll tell you later. I'll remind you at the end to work on it. Now, in practice, the method that I gave doesn't necessarily give just one tree. It probably gives a handful, a small handful, right? So you end up maybe, let's say, about 1 in a million chance that a second component would have the exact same tree, okay? So if we had 5 different components and you generated 5 different trees, the chances of all of them being the same would be about 1 in 10 to the 24. Basically wouldn't happen, right? So here's 5 different components and all different trees, okay. So far, I think nothing terribly controversial. Let's look how this looks in biology. First, I'm going to choose 11 animals. Here they are. It's a kangaroo, a rabbit, a rat, a rhesus monkey, a chimpanzee, a person, appropriate person, dog, horse, pig, sheep, and cow. So I've made it 11 animals. So with 11 animals, there's more possibilities. There's now 655 million possible binary trees. Okay. And for components, you might think that we would use, or we could use like hearts, lungs, liver, I'm not a biologist, stuff like that. But we can do much, much better with components. We can use genes. And so, for example, the gene for hemoglobin A. Hemoglobin A is something that's generated across all of these animals. They're all mammals, of course. And they're recognizably the same gene, recognizably doing the same thing in all these things, just like our fuel injector. This is a huge advantage because it's digital data. So it's not, engineers going, well, this one's got a little bit of a hook. It's fairly unequivocal. So you can do this analysis pretty precisely. And it's been done. People have done this. So this is what it looks like. Hemoglobin A, this is the tree. Okay? Now, we need to start thinking about what this means. And that would depend on what our theory is. So we have 2 different theories that we're going to look at. Okay, this is a little tongue-in-cheek. But we have the sort of creationism design theories or the evolution theories. In creationism, these theories postulate that the similarities in the DNA exist because there's a designer who's reusing it. One of the chapters in the book that I respond to makes this exact argument, a man called Richard Spencer. Not the egregious one. I think he's a normal one. Anyway, so he made that postulation. And as such, you would expect there to be no special meaning to the tree. It's just whatever the designer did, right? And so each different gene will be kind of quasi-randomly picking from this huge solution space of 655 million different possible trees. Evolution, of course, is different. It says that this happened because of common descent, and therefore this tree is the phylogenetic tree. That's what we're looking at. And therefore, evolution makes a far, far stronger prediction. It says each gene, regardless of which gene you use, will give you the same tree. Okay, so we can have this kind of game, right? Roll up, play the game of life. 655 million possibilities on this roulette table. We're going to spin it 5 times. If it comes up with 5 different answers, which is what you would always expect, that leans towards creationism design theories. If it comes up with the same tree 5 times in a row, that leans towards evolution. It's a pretty bold prediction. So here's the tree for hemoglobin A, as I showed you earlier. Here's what it is for hemoglobin B, fibrinopeptide A, fibrinopeptide B, cytochrome C. They're all the same. So this is a monumental achievement. I mean, can you imagine being on the team that got all these DNA sequences from all these different animals, figured out the genes, put them into this program to analyze the genes digitally and figure out this tree? It's a huge achievement, and yet it's just a tiny part of the picture. This is a picture that was generated with 3,000 species, automatically done from their RNA, using this exact method. So that was my first one. Everyone with me so far? Good. Okay, next one, apes and the chromosome. Or we should really just believe him. We'll see what I mean by that just now. So, quick reminder about chromosomes. They are if your DNA is a book, chromosomes are the chapters. Okay, they're the bits. They're all next to each other as we go. So, a book can be divided into many or few chapters. You know, from the common fruit fly, which has 8 chromosomes, the kingfisher kind of bird has 132 chromosomes. It's all over the show. I wrote a book. Did I tell you that? It's got 53 chapters in, so it makes it somewhere around a silkworm. Maybe I shouldn't have brought that up. So the chromosomes, we don't need to know much about them, but this is a representation of a chromosome during replication. Okay, so it splits at the ends, and then the final bit that separates is in the middle. So the thing that you need to know about chromosomes for now is that at the end there's a telomere, and in the middle there's a centromere. Okay, telomeres at the end, centromere in the middle. So when we see adjacent chromosomes, you'll see that there's a telomere of the last one, and then the next one has the next telomere, and so on. Now, one thing I want to point out to you is this bit here. Okay, we, as you know, have 23 pairs of chromosomes, famously 23andMe, and so 46 chromosomes, 23 pairs. Chimpanzees and gorillas, which we saw from before were our closest living relatives, have 48. So that's a bit of a puzzle, all right? So our nearest living relatives have 48 chromosomes, we have only 46. That was that was a while ago when my wife and I were traveling up in Zambia. There was a chimpanzee sanctuary. And I don't know exactly how this happened, but anyway. The evolution predicts, is a very specific prediction, that the only way this would happen, well, the most likely way this would happen, is if 2 chromosomes merged at some point in our recent evolutionary past. Okay? So, there's 3 billion base pairs in human DNA, and so scientists went searching for telltale signs. Now, here's what they found. There's our human DNA. It's cut off the telomere, but you have to trust me, there's a telomere on the left-hand side there. So the green ones are the telomeres going along, those are the 23, each one representing a pair. So this chromosome number 2 is the longest of the chromosomes in the human DNA sequence. And look closely at it while I push it on. Something's going on there. Let's zoom in a little. So there's human chromosome. Along the bottom there's the number associated with the base pair. So we have all these numbers. And when we look closely, what we see is 2 vestigial telomeres and 1 vestigial centromere, right there in our DNA. In other words, this looks like what it probably is, a recent merger of 2 chromosomes. Now, scientists, I can tell you, were not at all surprised by this because the corresponding position in chimpanzee DNA looks like that. And so, as you would expect, there's the 2 chromosomes that exist in chimpanzees and clear evidence in our own chromosome, chromosome number 2, that is recently merged. So, evolution makes very detailed predictions that are beautifully fulfilled. Alternative theories about this either don't make a prediction or, they make it wrong. We don't need fossils to confirm evolution. It's nice, it's great that we've got them, weird accidents that happen in history. And certainly not trying to stop anyone. There's wonderful stuff going on there, but it's as written as plain as day in our DNA, which, by the way, was discovered hundreds of years after Darwin thought of evolution, right? So if there's a designer, he has gone to so much effort to make it look like he was not involved, that at this point it would be rude not to believe him. Okay, so maybe that's slightly controversial. So substrate independence, that's my third point. one of the things that excites me, especially as a condensed matter physicist, is seeing what we call emergent behavior, right? So a set of simple rules creating complicated behavior when you apply it multiple times. So in condensed matter physics, you see this in magnetism, you see it in superconductivity. We all see it when we see birds fly overhead, flocks of birds, which people used to think maybe there's some kind of weird ESP going on that birds can do this, or shoals of fish can do this, right? But no, there's just a small set of simple rules that they're all following, and we can simulate the behavior very, very closely. We see it in routers on the internet, we see it in the stock market, right? The question is, what are the simple rules that drive evolution? So Daniel Dennett wrote a lovely book in which he says evolution will occur whenever and whenever three conditions are met: replication, variation, and differential fitness, I call selection. So replication, mutation, selection. If you've got those three, you've got evolution. And out of this, you get quite complicated behavior emerging. So you see cooperation, you see symbiosis, you see parasitism, you see mimicry. I want to give just a couple of examples of mimicry that occurs in nature. On the left there, you see the pipevine swallowtail butterfly. It, I guess, eats poisonous plants and becomes poisonous itself and very unpalatable to birds. I personally find butterflies unpalatable at the best of times. The spicebush is a different species, but it looks very much the same, and it's not poisonous. So as long as its population numbers stay relatively small compared to the swallowtail, it gains the advantage without having to ingest all the poisonous plants. You see, in this part of the world, you see this as well. You see rattlesnakes and you see gopher snakes. Gopher snakes deliberately try to look like rattlesnakes, even rearing up in the same way. This on the left is very dangerous and scary. This is just faking. There's nothing there. Even in our own species, we see psychopaths. Psychopaths are mimicking normal, empathetic, cooperative members of society, right? And getting all the advantages of being part of society without really having any of it. So evolution would predict that this kind of thing happens, of course, because there's this opportunity, this little niche that can be filled. So why wouldn't it? It's harder to understand if you take the view that everyone is a child of God, that 1% of the population just are not empathetic. So according to Without Conscience by Robert Hare, fantastic book as well, he says about 1% of the US population are psychopaths and about 25% of the prison population. So it tells you where they end up. Others of them end up, I think, in the upper echelons of of society. Anyway, we won't get into that much more now. So, I said evolution occurs whenever you get replication, mutation, and competition. We first discovered this in DNA, but there's no reason that it has to be in DNA to work. It's not necessarily biological. The substrate does not matter. So this is the idea of substrate independence of this phenomenon. So a simple example, you look at words, right? Words are repeated, they're replicated through speaking or through writing. They mutate in pronunciation and spelling, and they're selected by the usage. In this case, and most cases, it's not that one is better or worse. I would say pronunciation. Many of you might say pronunciation. But that's just, it's a question of what was selected by the community, which one stuck. And Darwin himself noted that the formation of different languages and of distinct species, and the proofs that both have been developed through a gradual process, are curiously the same. He noted that the evolution of words and the evolution of species is very similar. So we know that words are ideas, and we can see them evolving. It's relatively uncontroversial. Does science evolve in this sense? There's an idea. It's not in DNA, it's in our brains, it's in our collective brains. So does science evolve? There's two questions there. Does the scientific method evolve? And does science itself evolve? The first one, I would say the answer is yes. This is a kind of evolution of the same sort that dogs go through, right? They are selected by us for a specific trait, to be friendly in that case. In this case, we replicate the scientific methods, we compare alternatives, and we produce theories. We select for methods that produce theories that explain the data, right? So in that sense, it's something that we have done rather than nature has done, right? But nonetheless, it's evolved and it's improved. And does science evolve? Absolutely the same. Theories are suggested and published, new data is gathered, and we adjust theories or we create new ones, but we are selecting for theories that explain the data, right? So that is the whole point of the scientific method in a way. We've created a system that selects for ideas that explain empirical data. It's somewhat banal to think of science in these terms because we had so much control over it, right? It's not as crazy as biological evolution. But I think a more interesting question and related question is, did religion evolve? And again, we have the same thing. Did our religious tendencies evolve? And do religions themselves evolve, right? Our religious tendencies, they exist all over the world. Every human, every part of the world, regardless of where they are attracted to religions for some reason. It's a fascinating topic. And so it's clear that our religious tendencies evolved. What's not clear is why. It could be that it's a parasite that preys on our mind. It could be that it's something that helped us in some sense. The sweet tooth theory, the idea that in the old days, when we were walking on the fields of the Serengeti or something, if we found a source of sugar, we would just eat it. That made sense. So see the sugar, eat it. Right? Nowadays, that's proven problematic for us. We see sugar, we should control ourselves, but we have the evolutionary urge. And so perhaps something like that is happening. So one of the two major popular theories here is something like the hypersensitive agent detection device, HADD, where if you're walking in the Serengeti and you hear a rustle in the bush, you have two options. You can say, hey, whatever, and sometimes that'll be okay, and sometimes you'll be lion food. Or the other hand, you can say, I'm out of here, I'm assuming there's something there, and if it was wind, well, doesn't matter, right? If it was a lion, you got out of there. And so that tendency to assume that there was an agent behind every phenomenon that we see would be selected for very aggressively. And so you would see something like, eventually you start saying, well, what about the rain? That must have an agent behind it. What about lightning and so on? So that's one set of theories. The other one is that as we got more communal and more cooperative, that religions evolved and the tendency to follow religions evolved in order to keep people in line, right? Keep people cooperating. So fascinating area, not something that I have much more to say on, but well worth considering. Do religions evolve? Well, there it's fairly unequivocal, right? We see this happening. We see religions replicating. We see syncretism where aspects of an adjacent religion get pulled in. We see new variations being selected, and so religions grow or go extinct depending on whether people practice them, right? So the problem is that this is different from science. Science, we were controlling and we were specifically going for theories that explain the data. Here we've got some vague thing going on in our evolutionary ancestors, and so we don't exactly know why some religions are great and why others aren't, right? It's just something that happens. But the notion that a dearly held belief could be more the result of your mind providing fertile soil for it than an objective measure of its accuracy should be disquieting. Right. That was from my book. Did you guys know I wrote a book? So here's a graph from some guy on the internet, also not peer-reviewed, but again, just to show the idea. Like, we know that Christianity and Islam both came from Judaism, probably with some Hellenistic mystery religions thrown in. We know that Christianity evolved into Catholicism and Eastern Orthodox, both of which will tell you that they are the original and the other one is an offshoot. We know that Protestantism evolved because a king wanted to get divorced, and I assume some other stuff. You know, this is something that we see all the time. So it begs the question, why is Christianity successful in the sense that it's practiced widely, right? And firstly, the question is it successful? I would say maybe not, in the sense that there are a huge number of variations of Christianity, most of which are barely recognizable to each other. But they sustain themselves with the idea that each variant sustains the notion that they're the only true Christianity and everyone else is kind of not really quite there. And so, if you're counting numbers, people will count everyone. But if you're counting people who you think are really Christian, well, it's just us. Probably just me. And which is exactly what you'd expect from an evolved system, right? Lots of different variants fitting in with different cultural niches. So I think a way to think about this is to flip the thinking around and say, don't think of this as the qualities of a single religion, but think of the marketplace of ideas. Huge numbers of religions all competing, lots of different characteristics kind of evolving, people trying them out, saying, hey, we should all just run off a cliff. And that religion turns out not to work out so well, right? But the characteristic, I think that just by common sense, is going to be very common, is that if you're told to believe by faith, and if you're told to go out and get more followers, you're going to have a successful religion. And I think there's other traits that Christianity has. I think one of the things in the early days was that it preached a spiritual victory rather than a physical victory. So in the Jewish Messiah set, there were a bunch of messiahs predicted to come, a whole bunch of them wandering around in first century Palestine. But most of them were saying, we're really going to be ruling this world pretty soon. And when that didn't pan out, they collapsed. But Christianity had a mutation that said, no, you can't even see this victory. It just happened up there somewhere. I'm not going to go through all of these, but one of the other things that you do see is a mimicry of science. So science has been very successful in the modern era in a way that it certainly wasn't when Christianity was formed. But Christianity has an adaptability. And so you see both, I think this is a subset of undermining rationality, but the idea that something like intelligent design promotes itself to look like science. So it imitates the various different patterns that science has. So you can mimic a scientific convention, the language that's spoken and the uncertainties and all that sort of stuff, without having scientific rigor. And I think in a modern era, pseudoscientific ideas survive precisely by doing that, right? So, summary, replication, mutation, and selection. It's an incredibly powerful idea that in the sense that it encompasses a huge amount of explanatory power, let's say. One of the things that sometimes comes up is selection. Some people will say, if you're just having random mutations, you won't get anywhere. Scientists agree. It needs selection as well as mutation, right? It's been applied successfully in a bunch of different places. Obviously, biology is the first one, but we see it's a good way to understand language, traits, other characteristics that we have. It's used extensively in computational techniques, so at least in principle it works. We use it in farming, animals and so on. And I think understanding religion as a natural phenomenon is a far more compelling way to examine it, which I think is the case that Daniel Dennett was making in his book. So that is my third point. But wait, there's one more thing. So I was visiting my sister in New York just before my book was published. Did you know I was writing a book? And she happened to have a publisher visiting her, and she received an email, and she was being kind of awkward about this email, right? And so I cajoled her a little bit, and she eventually read it. It was from someone I won't say who. And she says, we hear that Glenton is in New York promoting his book, Evidence Considered, A Response to Evidence for God. We believe that he is a harbinger of the end times. And so my sister sort of finished the email and looked up to see how I responded, and I said, "This is fantastic, they know the name of my book." And the publisher who was in the room just rolled her eyes and said, "Typical author." So that's my one more thing. We're going to do a shameless plug for my book. So firstly, it has 53 chapters. So if you go out and read one chapter with every coffee you have, this is the most gratuitous graph in the whole presentation. So the book cost over there, the average cost of coffee per chapter, you can vary from anywhere from 0.5% to 7.5%. Either way, it's not that much. 53 chapters that you can fit in an acrostic. So this is the first kind of public reveal that there is an acrostic across the 53 chapters. This is not my book. This is Psalm 119, which has a much more boring acrostic because it's just the letter Aleph repeated many times until the next section where it's Beit or whatever the next letter of Hebrew is. Mine actually spells out something more interesting. In the original book, Evidence for God, that I respond to, William Dembski writes a chapter that he calls Head in a Vice. I still struggle to believe that he did this. He envisages putting a Darwinist, what he calls a Darwinist's head, in a vice and subjecting them to a bunch of questions. The insensitivity of that is kind of obvious. But, and he just presents the questions. He does, so I suppose you're supposed to imagine this poor Darwinist being tortured and struggling to come up with any answers. But anyway, I answer them. which is fun because there's an interesting twist in the tale. Just the way he asks his questions leads to a very unexpected answer. The book contains many examples of evolution of Christianity. This is the story of the fig tree, but there are many others. I don't claim that I've got everything right, but the evidence for the evolution is there for all to see. And if you are in a situation where someone hands you an apologetic book, Evidence for God, Mere Christianity, The Reason for God, Cold Case Christianity, The Case for Christ, Evidence That Demands a Verdict, or something else, there's a bunch that more or less the same material rehashed as far as I've seen. You can hand a book back and say, here's an alternative view. So that's my talk, and I think I'm bang on half an hour.